Welcome everyone to this SK Time meetup today. I'm happy to welcome Luca Castri from the University of Lincoln. He will present about his package CausalFlow, a unified framework for causality in time series. Thank you very much for joining. I'm very much looking forward to this presentation. Over to you, Luca.
Thank you. First of all, thank you for having me and for inviting me for giving this presentation. I will present myself. So hello everyone, I'm Luca Castri, a PhD student from the University of Lincoln. And today I will be presenting a framework that I've been developing since the beginning of my PhD. And it's called CausalFlow. So this is an overview of what I'm going to present. I will start from a very simple and brief motivation behind this work, and then I will give a high-level explanation of the main parts of CausalFlow. And then I will go more in detail about two specific causal discovery methods, in particular F-PCMCI and CAnDOIT, that I developed during my PhD. And finally, I will explain a random graph, which is a useful tool when you need to evaluate and benchmark your causal discovery method. Then I will conclude my presentation summarizing what CausalFlow is and future direction. So for who is not familiar with causality, what is it? So causality is the science that studies the cause and effect relationship between events. And nowadays it's divided into three main areas. So we have causal structure learning, which starts from a data sets and a predefined set of variables, and aims to learn the causal structure between them. Then we have causal reasoning that starts from a known causal structure, a known causal model, and aims to exploit this causal model for forecasting on or decision-making tasks. And very recently, another area has been introduced, which is causal representation learning, that is similar to the first block, but here we only have a data set, and we don't have a predefined set of variables. And the goal is to learn the variable that best represent your data and the causal structure between them. So in this presentation, I will focus mainly on this part, so the causal structure learning block. So with this slide, we arrive to the main motivation behind CausalFlow. Today, we have many causal discovery methods that are available online for time series data. And the problem here is each method tends to have its own input and output format, and often its own graph representation style as well. So what we so this makes it hard to compare results and integrate different methods, and we need a framework that unify this whole pipeline. So that's why I developed CausalFlow, and it represents a collection of causal discovery methods for a time series. And right now it includes 10 different methods, 2 of which have been developed by me during my PhD. And they are F-PCMCI and CAnDOIT, that I will explain more in detail later. And then it also includes a random graph, which is a tool able to generate a random system of equation with the possibility also to include hidden confounders and generate observational and interventional data from this the generated graph. And in this presentation, I will focus on these three elements. But before that, let's see a very high-level representation of causal flow. So let's start from the three main, the three different inputs format that our framework can handle. And here we have a NumPy array, a pandas data frame, or simply a CSV path. And from this input formats, basically, we can build our data object, which contains various properties related to our data. For example, the number of variables, the t, which is the length of our time series, and so on, and also methods that are useful for visualizing our data or manipulating them before the actual causal analysis. And then we have the discovery block, where, as I already said, we have 10 causal discovery methods that we can use for our discovery process. And then we arrive to our graph object, which is a class that contains basically a dictionary representing our causal graph, from which we can derive 4 useful 3D matrices. Why 3D? Because they contain information related to the relationship between variables in each layer. Each layer is basically a squared 2D matrix, and we have many layers as the dimension of the time window that we consider in our causal analysis. And so we have the skeleton matrix that contains ones where there is a link between variables, and it is the first one. Actually, I don't know if you can see my pointer. And then we have the value and the p-value matrices that contains the strength of the causal relationship and the confidence associated to each link. And then finally, we have the link matrix that contains information about the link type. As you can see, the simple arrow, or the arrow where we have a circle symbol at the tail that describes, for example, uncertainty. Then we arrive to the graph plot part, and here we have a summary graph and a time series graph, and the latter is basically equivalent to the summary graph, but it shows the whole time window that we consider in our causal analysis, with the same set of variables that are repeated for each time step, and the causal link between them. So these are the 3 main blocks that compose causal flow. And now let's introduce F-PCMCI, which is the first causal discovery method that I developed in my PhD. But before doing this, let's first explain its predecessor, which is PCMCI. And this also gives us the motivation behind F-PCMCI. So PCMCI is a well-known state-of-the-art algorithm from a Python package that is called Tigramite, maintained by a German group led by this guy. And so let's consider this problem with for example, 4 variables, X, Y, Z, and W, and a time window composed by three time steps. So t minus 1, and t minus 2. And our goal is basically to find the causal relationship between these variables, also between time steps. So the algorithm, the first step of PCMCI is the PC algorithm. So here, the first block, which aims to retrieve the causal structure between this variable, considering only lagged dependency. And it starts from a fully connected graph, so exactly like this, and it reaches a first version of the causal structure, then that then needs to be validated by the second part of the PCMCI algorithm, which is the MCI test. And basically, this test, this MCI block test link by link, and performs a conditional independence test considering only the parents of the involved variable. So here, for example, is trying to validate this link that was found by the PC block between Z and the X variable. And in doing this, it considered the parents that he found at the previous block. So X, Y for X, and W at t minus 2 for Z at t minus 1. So the main issue of this method is its computational complexity, which depends on the number of variables and the dimension of the time window, this tau max. And so my question here was, is it possible to improve this process? So if we consider this example with 5 variables, where one of them is isolated, E, and so my question here was, is this variable useful to understand the evolution of the system, or can be just neglected? So the goal here was to create an only one solution to select first the most important variable, and then reconstruct the causal model. So here we have the main structure of F-PCMCI that extends PCMCI by adding a block before the actual causal analysis that basically filter the predefined set of variables that is given in input. And it's basically divided into 4 main steps. It starts from a predefined set of variables, like its predecessor, and but before going into the causal analysis, basically it removes the irrelevant variable using a filter that is based on transfer entropy. And for who is not familiar with transfer entropy, it is a measure that quantifies the flow of information from one variable to another, specifying the direction of this flow. Then basically we can use this filter not only to reduce the number of variables, but also to build an hypothetical causal structure between them, as you can see here in the example. So basically we have here in the example 4 variables in the predefined set of variables X, Y, Z, and W, and the filter basically reduced the number of variables to 3, and also outputs this hypothetical causal model based on the transfer entropy. Then these 2 basically are given in input to the final block, which is the causal discovery block, which basically runs the PCMCI algorithm. And basically by using this framework, by using this filter, F-PCMCI enables faster and more accurate causal discovery. So we evaluate F-PCMCI first on a toy problem here, and like this one, and basically it includes a isolated variable here, x6, and you can see here it doesn't appear in any of the other equation in the system. And these are the two causal models from left PCMCI and F-PCMCI. And we can see that F-PCMCI was already faster compared to PCMCI that took more or less 3 times the time for this causal analysis. And beyond being faster, it was also more accurate. So as you can see, PCMCI found a link between X6 here and X5. That is wrong, while F-PCMCI was able to remove from the beginning, thanks to the transfer entropy filter, the X6 variable, since it was isolated and irrelevant here. Then we also evaluated our F-PCMCI with datasets, with a dataset containing data about brain networks. And also here, F-PCMCI outperform PCMCI. Then our goal here was to basically use the F-PCMCI to model human spatial behaviors and predict them. So we extracted data from a dataset that is called Thor, that contains data about human spatial behavior in a warehouse-like environment, and run the causal analysis with F-PCMCI, and then embed the structure of the causal model that we found into an LSTM network for the prediction of the time series. And we repeated the same process also with PCMCI to compare the two results. And here you can see again that F-PCMCI was way faster compared to PCMCI, and also the causal model from F-PCMCI appears way cleaner compared to the one on top. The problem here was we didn't have a ground truth causal model. So basically what we did was we used the prediction accuracy as a metric to evaluate the accuracy of our, the correctness of our causal models. So we can see from the bar chart that the prediction obtained by using our the causal model from our approach was the most accurate one, which is the bar at the bottom. So here I presented the F-PCMCI, and this is the paper associated with this algorithm. And here we also have the main limitation of F-PCMCI, and also basically all the causal discovery methods for time series data. Basically, they only use observational data. These observational data are often insufficient to retrieve the correct causal structure when the latter is complex, or we are in presence of a hidden confounder. So our goal here was to create the first causal discovery method for time series that was able to incorporate both data from observational and interventional data. Here again, just a very simple example with a toy problem. So here, let's consider this system of equation where we have L1, which is a hidden variable, and it is a hidden confounders that confounds these two variables, so x0 and x2, and we can represent this relationship between this spurious relationship between these two variables by using this bidirected link. So using F-PCMCI for the causal analysis, which is an extension of PCMCI that handles latent confounders, basically we can obtain this causal model that contains the correct bidirected link, but it also contains this link between X2 and X3, between X2 and X3 with an uncertainty, which is this, which is represented by this pink circle here at the tail of the link. And so, although here the system of equation was quite simple, F-PCMCI was not able to retrieve the correct causal structure. So we introduced CAnDOIT, that stands for causal discovery with observational and interventional data from time series. And let's consider this example. So we have this three variable system, A, B, C, and we want to execute an hard intervention on the variable B, meaning that basically the value of B no longer depends on the variable C, but it's decided by the intervention. And the problem of incorporating both data in the causal discovery process is that so basically our final causal model must be faithful to both cases. So it must contain the link between C and B in the observational case. Instead, this link must be cut in the interventional case. So how can we do this? By using, by using context variable. These context variables are basically meta variables that do not depend on any other variables in the system. So they are called exogenous, and they are useful to inject the interventional data into the intervention node. So in this case, B, without cutting its link from its parents. So taking again the example that I showed before, CAnDOIT using the interventional data injected by the context variable here, CX2, that models an intervention on X2, is able to give us the correct causal model. As you can see, there is the bidirected link between the confounded variable and also the uncertainty at the tail of this link between X2 at t-2 and X3 at time t disappeared. So again, here we evaluated CAnDOIT in a robotics scenario, in particular in a manipulation scenario, or where basically we have this scenario where the end effector of the robot is a camera that views this white cylinder and the gray floor and a red cube in the cylinder. And the brightness of the colors seen by the camera depends on various factors, like the height of the camera, its velocity, and its distance to the cube. Indeed, if we move the robot inside the cylinder, basically in this scenario, all the colors seen by the camera will appear a bit darker due to the less amount of light, basically. So here we wanted to create a scenario in which we model the brightness of the color of the floor, so FC, and the color of the cube, CC, depending on these factors, and also where we have a confounded variable, in this case the camera height. So now let's consider this confounder hidden. So we expect again a bidirected link between the two confounded variables, in this case the two colors, so FC and CC, and generating data with this simulator that is available online that is called Causal World. So we were able to recreate the scenario that I explained in the previous slide, and running the causal analysis with F-PCMCI, we obtained the link between the two colors with two particular uncertainty, as you can see with these two pink circles. And basically, this uncertainty represents two possible links between these two variables, and both of them are wrong, basically. Now, if we consider if we perform an intervention on the color of the floor, as you can see here, we generate again data using causal world, but in this case, the color of the floor was not anymore depending on the hidden confounder, but was manually set on green. By using CAnDOIT for our causal analysis, we were able to obtain the correct causal link, which is the bidirected link between these two variables. So to conclude, we presented the first observational and interventional based causal discovery method for time series, and this is the paper associated with it. And here I just want to give also, I just want to present the final tool that it's contained in CausalFlow, that is called Random Graph. Random Graph basically is a tool that is very useful for generating random causal structure and data associated to this structure. And this is very useful when you need to test or benchmark your causal discovery methods. And it gives you the possibility to set all these parameters. So the time series length, the number of observable variable, sorry, the link density, which is basically the number of parents for per variable, the number of hidden confounders, etc. And also, very important, also the possible operators linking all these factors in this equation that we are building, and the functional forms for all the items contained in this equation. And here, just an example. Here in the black block, you have an example of the code generate this random graph. So we basically want to have a random causal model that is generated with 5 observable variable, and the time series are composed by 1,500 samples, and so on. And this is basically the system of equation that this tool generated, and also this is the random causal graph that was generated from this tool. And as you can see here, we have 5 variables from x0 to x4 that are observable, and also here we have 2 hidden confounders, h0 and h1. And from this, basically from this causal structure that we are able to randomly generate, we can basically generate observational data, time series data, as you can see here, composed by the number of samples that you specified here. And also this is very important. If you want to basically perform an intervention of a specific variable of your system, you can do it, and you can also specify here the length of the intervention. Why this is useful? It is useful because basically you can intervene on one of your variable, in this case x4, and you can see the effect on all the other variables composing your causal model, basically. So to wrap up, basically what is CausalFlow? CausalFlow is a unified framework for causality in time series domain, and basically I try to simplify this pipeline from inputs, discovery process, and causal graph into a unified framework where you have the same input format, the same output format, and all these causal discovery methods under the same umbrella, let's say. So future direction, it's always important to keep this framework updated with new causal discovery methods, and it might be very interesting to build like an interface for this framework for who is not very familiar with the code. And also right now this framework supports only the discovery part, and it might be really interesting to extend and introduce also the reasoning part, like for example do time series prediction based on the causal models that we are able to retrieve. Thank you so much. Thanks to Franz for inviting me again. And if you have any question, I'm more than happy to answer.